So in this video, I'm going to move on to question 2 of the assessment. So we're going to be looking at the diffraction grating equation questions. So first thing to look at is we've got our diffraction grating equation, which is this one you can see right up here at the top. So we're going to be looking at the first order here, so that's why the n has disappeared from the equation. So we've got the two slits, so we're zoomed in looking just at two slits, and it wants us to label the distances and d and lambda. So the thing to remember with this, when you're deriving the diffraction grating equation, we're assuming these are travelling parallel to each other, so if they're going to constructively interfere, their path difference must be a multiple of the wavelength. And if it's a first order beam, that means the path difference must be the wavelength. So that is going to be this length along here, because that's the difference in distance travelled by this one and this one. Like other than that, it's the same. This is the extra bit, so that must be the path difference. And d is your distance between your slits. And we can double check that we've done this right, because if we're using some trig, d sine theta is indeed equal to lambda for this right angled triangle we've made here, so we know we've done it correctly. So then it wants us to state and explain what happens to the value of theta for the first order beam if the wavelength decreases. So theta, first of all, let's calculate this, is calculated by doing the inverse sine, and then we're going to have lambda over d. Okay, so here, what we can see is that if we decrease the wavelength and keep d constant, we're going to be taking the inverse sine of a smaller number. So the way to think about this is think about what the sine graph looks like in the first 90 degrees. It looks like that. So if we get a smaller value of sine theta, that would also mean we have a smaller theta as well in this section up to 90 degrees. So from this equation here, we can see that as wavelength decreases, this overall function decreases, which causes theta to decrease as well, and we're keeping d a constant throughout this process. Okay, so that's that one, so let's move on to the next question. So we've got a diffraction grating being used with a spectrometer. So spectrometers are used to analyse the wavelengths or the frequencies or photon energies emitted by certain elements. And we're looking at 6 different line spectra. We need to identify the 3 elements that are present. So essentially we're looking for these lines to correspond with lines in these ones. So you can see with mercury, these ones all match up here, so mercury is definitely one of them. With strontium here, if we see here, we've got this line is in strontium, and it's in there, so that's okay. That one's in there, so that's okay. However, these ones here do not have corresponding ones in there, so strontium is out. If we look at calcium, it has a line there, but there isn't a line there in the star, so we can eliminate that one as well. And if we look at sodium, we've got these ones very close together. There are no two correspondingly close together here. There you can see they're much further apart on the star X, so it's not going to be sodium. So by process of elimination it should be the last two, but let's just double check. Those match up there. We've got a match down there, we've got a match there, so that's all fine. Then we've got matches there, there, and there. So again, these last two are fine, so yeah, it is indeed these last two that we need to select. Okay, so the diffraction grating is used to measure the wavelength essentially. So we're using a diffraction grating with 300 slits per millimetre. So the first thing we need to do before we can calculate the distance is turn that into slits per metre. So it's 300 per millimetre would be 3 times 10 to the 5 per metre. So then if we want to calculate the distance between them, it would be 1 over that. So 0, 0 times 10 to the 5. And what we can do is we can type that into the old calculator. And you end up with 3.33 times 10 to the minus 6 meters, giving your answer to 3 significant figures, because this number here you've been given in the question is 3 significant figures too. We want to calculate the angle of the first order. So got n lambda is d sine theta is the general equation. We can get rid of that because we're looking at the first order. So theta is going to be inverse sine lambda over d, which is going to be inverse sine. So we need to look up where is p. So each of these is 10, so it's halfway between 40 and 50, so let's say it's 545 times 10 to the minus 9 and divided by 3.3, not using the rounded version, times 10 to the minus 6, giving us a value of, type that in, so that's our value of d. And then we do 545 times 10 to the minus 9 divided by answer, inverse sine of the answer, and we end up with 9.41 degrees to 3 significant figures. You could get a range of answers depending on what value you put in here, so you might have a range of different answers. This question accepted anywhere between 9.4 and 9.6, I think, so anything in that range is absolutely fine. And that concludes this question number 2.